Okay, let's continue. And sorry, I didn't upload for a while. So I was busy in giving tests and stuff, and yeah, it was pending. So we did till 60, I think. Question number 60. Okay, let's go to question number 61. So question number 61. Minimum temperature at which the following reaction will be spontaneous. So A reversible, B, and delta H is given, delta S is given. So the thing is that for constant temperature and constant pressure, when your Gibbs free energy, the change in Gibbs free energy, that thing is zero, the reaction becomes reversible. And when it's less than zero, the reaction becomes spontaneous. You want this to be less than zero. And by the minimum temperature, they mean the equilibrium temperature, right? At which this reaction just becomes reversible, right? And they didn't give any concentrations or whatever. So yeah, if they don't give us concentration, that just means delta H and delta S are the only thing that we have to look for. These will be assumed to be constant, right? And what that means is that even though this thing is delta H standard, right, this is only for 300 Kelvin, you can still use this for different temperatures. So in that case, delta H minus T delta S must be equal to zero, right? That is when this will become reversible, right? So like this could possibly be something like a phase change. So for example, ice melting into water. In that case, you have delta H, delta S almost constant. Yeah. And you also don't have the concentrations x the activity. The activity stays constant, right? Because it's just pure phases. So this could be a phase change, right? Cool. So yeah, this just means temperature for reversibility. That thing is just delta H upon delta S. So for higher temperatures, this will become spontaneous. And what is this? It's just 50 in kilocalorie per mole upon 100 in calorie per Kelvin. Huh. Per mole, of course. Because yeah. And yeah, well, also it's kilo, and that's a problematic thing because this is going to be times 1000 in that case. So there we go. It's just 1 by 2 times 1000, which is 500. So 500 Kelvin. And that's option B. Question number 62. When equilibrium is attained, delta G standard equal to 0. What is this? E standard equal to 0. I think E means energy over here. So no, when E standard, and what does E actually mean? Delta E would make sense because I think it means the energy of the reaction. So no, the energy of reaction, that being 0, that does not mean that it's reversible. So yeah, delta G equal to 0 is the condition A. Question number 63. Delta G at 25 degrees Celsius for this reaction is okay, hence thermodynamic equilibrium constant is right. So they just gave delta G, find the thermodynamic constant. So you know that delta G is basically delta G some initial condition plus RT natural log of, I don't know. Well, actually, no, instead of writing it like that, you should probably write it like this: RT natural log of Q upon K. So when Q is less than K, delta G is negative, so it's spontaneous. Yeah. And we want delta G standard for delta G standard, this is not power 0, it's just a symbol for this being standard. For standard, it will be R into 300 Kelvin into natural log for, so Q will be 1 over here and this will just be K. So that is negative R into 300 Kelvin. Oh wait, standard, that is dependent on temperature, right? It's still dependent on temperature. So when they say standard, they mean standard pressure, standard concentrations. They don't mean standard temperature. Okay. So this will be negative RT natural log K upon 1, and this 1 has units and everything. Okay. If you assume that equilibrium constant has units, then yes, it has units. Otherwise, you could just write it like this. All right, cool. So yeah, If they gave us what delta G is, we can figure out what K is from that. So K will just be e power negative delta G on RT, right? And what are the values? It's question number 63, right? So it's negative 16.5. So 16.5 kilocalorie or kilojoule per mole. So this time is 1000 because sorry. So this time is 1000 upon RT. So they don't give us R and T. 25 degrees Celsius. So at least T is given. So it's about 300 Kelvin. And R, we will say it's like 8.2 something. 8.2 in SI units. Yeah. And this should work. So notice that this thing is very much just the twice of this. So I'm going to write it like that. And yeah, so this will be 2000 upon 300, two zeros get cancelled. So 20 upon 3 and e power that. E power 20 upon 3. We know one thing. Like, you know what? I just learned this on the way that e power 3 is approximately 20. Like, e is less than 3. So this thing is less than 27 and it's bigger than 2 and that's like bigger than 8. And e power 3, it actually is in fact very close to 20. It's one thing we can use. Right. And then this thing will be written as, so 20 is like 21 minus 1. So this is like e power 7. No. Just not going to do that. E power 7. Not a good thing. Some other way. Question number 63. What are the options though? Oh, so it's in these things. Okay, cool. So you just have to guess a range for this. So it's definitely not like 1.08 because this is already 2.7 and then something that's bigger than 1, that is not 1.08. Can it be this thing? This is like 780. That is very big. Because like 10, okay, 20 upon 3, that is 6 point something, approximately 7 if you will. And it's definitely bigger than 2 power 6 in that case, and that would be 64. So it's bigger than that, and it's less than 3 power 6, which is 3 power 6 is like, wait, yeah, 2 power 6 is definitely 64, and 3 power 6, that is, oh no, that's 9 cubed, that's 729. That is very large. But hey, 780 is even larger, so that's not working, right? Okay, what could have gone wrong? It's just 20 upon 3. That should be like 6 point something. So, oh yeah, so 6 point something. That's why this maybe this is correct. So 7.80 to 10 power 2, 780. This thing is approximately 780. Huh. That's weird. So e power 20 upon 3, that's like e power 7 minus 1 upon 3, which is equal to e power 6 into e power 2 upon 3. Yeah, that's better. And e power 6 is like approximately 400. So 400 times e power 2 upon 3. That is 780. Or e power 2 upon 3. Huh. It's like 2.7 to the power of 2 upon 3. Not sure about it. Cube root of 2.7. No, how does that even make sense? Something that's close to that. Cubes. Okay, this is just spending our time on irrelevant things. So yeah, this is the only option that is sensible. I have to go for it because everything else just looks too small or too big. And even though this is not exactly what we think it is, but what can you even do? That's all they gave us. For an isomerization reaction, the temperature dependence of equilibrium constant is given by this thing. The value of delta S at 400 Kelvin is therefore. So dependence of equilibrium constant. Oh, the temperature dependence of the equilibrium constant. Whatever. It's just given by this thing. Okay, the value of, so it's like log base e, huh? So natural log k is this thing. So like natural log k upon natural log of e power 4. Sorry, not upon. It should be natural log k upon e power 4. Right. That thing is negative 2000 upon t. Well, this thing is just delta negative delta h upon rt, right? So that just means negative delta h. Delta h upon r is 2000, right? And what is delta s from this? Oh, uh, hey, that's weird. Delta s from this thing. What was that? Whatever. So they gave us this equation, but from this, can you figure out what delta s is? But you also know that k is rt natural log. Okay, sorry. G is right. So delta G is negative rt natural log k. So it's like standard. This is also probably standard, right? For that temperature. So from this thing you can figure out delta G. Yeah. So it's like just some temperature and cool. And of course you just have delta H is already given. So delta S is the only thing that's remaining in that case. Delta S, that will be delta G minus delta H upon, well, actually negative of that. So delta H minus delta T upon T. And what is this? Like, and I'm thinking the delta S is, okay, no, don't think of it like, okay, fine, let's try this thing. So delta H upon R. This looks okay, like you can find the value from that and stuff, but this has this temperature over here, and that's not something that is good. Oh, so you gave us the temperature. Well, then it's good. Then we can do it. So delta H upon R is just this thing. Then this thing is going to be R upon, so this is 2000 R. So it's like R upon T into, so actually no. This is so messed up. All right, this is 2000 R. That thing upon that, so it's like 2000 R upon T minus, and delta G is just this guy, so like plus all of that, so plus R natural log K upon T, right? Hey, I just realized that this thing, this natural log K is actually just delta G and stuff, so we could have got it directly from there as well, right? I mean, this thing is just negative delta H upon RT, and this thing, oh, yeah, this, so come on, why is this? Right, what was the thing? It's just natural log K is some factor natural log A. That's it. That's it. Just wait a second. Natural log K is natural log A minus delta H upon RT. But actually no, because yeah, that is the case, because at t equal to infinity you just have natural log A, and that would be correct, I think. Right, so that's the equation, and you also know that natural log K is just negative delta G upon RT. So putting that in there, you can just have like negative delta G upon RT equal to natural log A minus delta H upon RT. So delta H minus delta G is just RT natural log, or I should say this thing upon T is R natural log A. There we go. This thing is just delta S, right? So this will, now you know how to find delta S directly. So R times 4.0, because that's what natural log A is right there. So yeah, R times 4.0, and next time I'll just use this directly. What is R once again? We don't know. Uh, yeah. Oh, they have R in the option, so that's nice. So it's just A, 4R. We can share that. We can say that surely because we did the calculation. Question number 65. With increase in temperature, equilibrium constant of a reaction always increases, always decreases. Equilibrium constant, right? No, it may increase or decrease. Like you have that thing that it's dependent on delta H. If it's positive, then that means on increasing temperature it will increase. If it is negative, then it decreases. So depending on whether no, yeah. So D is correct. Question number 65 D. Question number 66. For this reaction, the equilibrium partial pressure P A is this thing, PC is this thing when the volume of the reaction vessel was reduced to such an extent that on establishing the equilibrium, the partial pressures of A and B were doubled. The new partial pressure of C would be reduced to such an extent that on re-establishing the equilibrium, the partial pressures of A and B were doubled. Hey, both of them were doubled and they were the same ratio, I think. Oh, so if these are the same ratio, but this is A plus B, so yeah, like how can that be it be in the same ratio? Because initially it's like 1:2 ratio for the moles, and then if you remove something from there, like yeah, the ratio should change, and if it doesn't change, that means that you didn't actually remove anything. And yeah, it's basically that there was no reaction when you did this decreasing volume, increasing volume thing, and it's still the same. So it's just PV equal to nRT for each of the gases, and there's no reaction happening. So the new partial pressure of C would be so P at wait a second. Partial pressures of A and B were doubled. You didn't give us anything about the partial pressure of B though. But you did say both of them were doubled, so it was still in the same ratio. Uh, okay, if this would have been like if A and B would have been both equal in moles, then this might actually work out. Yeah. But I really think that like PC should also just get doubled. It's gonna be 0.6 because no wait. You change the volume, your KC will change, your KP will also change. Okay, that's not the case then. Right, but at least now we know that both A and B had the same moles. So initially, so you had A, B, and C. Initially, A had like 0.15 atmosphere, B had 0.15 atmosphere, and C had 0.3 atmosphere. And if we were to revert this reaction all the way back, so all the way back to just having A and B, right, then this would be like A has 0.45 and B has 0.45 and C has 0. And now if we change the volume, so we change the volume, like for this guy it was such that no wait, why are we even doing this? No, why are we doing this? We already know that their pressure just changed to doubles, and now we just need to find what the pressure of C is. Hey, it isn't that hard because Kp is still the same. So call this thing X. That means X upon 0.3 squared. That thing is 0.3 upon 0.15 squared. And this thing now would just be 4. So X will be 1.2. There we go. So it's just 1.2 atmosphere. Right. This is, I mean, like, this is weird because as you see, the moles don't really match over here. And how can this be? Yeah, like how can this be? If you just started with only C, for example, then for this first condition you would just have, right, so pressures changed such that this happens. Fine, it can happen, it's not that it's impossible, it's not clear what happened. So we know the answer, it's just 1.2. Question number 66 is, yeah, C. Question number 67. Le-Chartres principle is applicable only to system in equilibrium, homogeneous reaction, system not in equilibrium, heterogeneous reaction, system in equilibrium, right? It doesn't matter if it's homogeneous or heterogeneous, it kind of still works, you know, like when you try to increase pressure, the system tries to decrease pressure. When you try to increase temperature, system tries to decrease temperature, and so on. The dissociation of this, okay, this is an endothermic reaction. So the following favor the forward reaction. So if it's an endothermic, increase the temperature. And over here, as you can see, when you go to the right hand side, your pressure increases because moles increase. So decreasing pressure, that will increase the forward reaction, because then it will, Le-Chartres principle, it will try to go to the right side. So adding Cl2, no, we want the forward reaction, that will just go backward. Compressing the gaseous mixture, that will increase the pressure, that's not good because then it will go backward. Increasing, why are there only three options? Oh, there is this fourth. Increasing the volume of the gaseous mixture, then that will decrease the pressure, and that would be a good thing because then it will try to go to the right direction. So C works. Decreasing the temperature, no, it's an endothermic reaction. So C, question number 69. It's 69. Okay, I skipped question number 68. Let's go for question number 68 now. Consider reversible reaction at equilibrium, the addition of Cn minus would. Okay, so fine. It will just revert back the reaction. So yeah, fine. Consider the reversible reaction at the addition of Cn minus. Reduce HCN concentration, no, it will increase it. Increase equilibrium constant, decrease S plus constant. I mean, C is just rubbish. B, yes, B works because it will go backwards and then you will have less H plus. And there's like dissociation of water as well, that might also play a part, but then just ignore that. Decrease, okay, D is also rubbish. So B, question number 68B. Question number 70. Which one of the following will favor the reverse reaction in a chemical equilibrium? Removal of one of the products regularly? Regularly? What does that mean? Oh, you want the reverse reaction, right? So no, don't remove the product. That will go for the forward reaction. That's not good. B is just not correct. C is correct. Adding negative catalyst, whatever that means. No, that just changes the path of the reaction. It doesn't change the thermodynamics. Okay, so the equilibrium constant is still the same. So it's C. Yeah, 70C. Question number 71. Consider the reaction PCl5 gives PCl3 plus Cl2 in a closed container at equilibrium. At fixed temperature, what will be the effect of adding more PCl5 on the equilibrium concentration of Cl2? So, oh, okay, fine. So, at fixed temperature, what will be the effect of adding more PCl5 on the equilibrium concentration of? So, yeah, like equilibrium concentration, huh? In a closed container, right? That's why you can talk about it like that. If it was a piston, for example, then it would just go up and the concentration would remain the same. So yeah, then if it's a closed container, then your concentration increases because it attains a new equilibrium, right? It increases. Okay, well, it's B. Okay, it's B. The more PCl5 you add, the more PCl3 and PCl and Cl2 you get. It's common logic. The effect of increasing the pressure on the following gaseous equilibrium reaction. So 2 plus 3, 5, and this is also 2 plus 3. So it remains unaffected, right? Hey, what is this thing? Why is this? Okay, so essentially it's just B going to A, but in a more complicated fashion. So yeah, it's got no effect on it. So increasing the pressure, right? So C. What's this question number 72? Question number 73. Uh, in which in which manner will increase of pressure affect the following equation? So one gaseous mole to two gaseous moles. So increasing pressure will favor the backward reaction, right? Will shift the in the forward direction? No, it will increase the yield of hydrogen. No, shift in the reverse direction. So B. For the equilibrium, uh, this increase of temperature would be what? Oh, okay. So this thing is like the heat produced. So 2NO2 that gives N2O4 plus this much of energy is radiated out, and that means it's an exothermic reaction. So increase of temperature that will favor the backward reaction. Favor the decomposition of N2O4. So B. Why did this happen? Question number 74 is B. Question number 75. Consider the equilibrium reaction. Apply Le Chatelier, whatever this name is, Le Chatelier principle, and check which one of the following is the correct effect of the increase in temperature. Fine. So delta H is negative exothermic. Increasing temperature will favor the backward reaction, right? And over here too, delta H was negative because this had more energy, and that's why it was able to give energy out. So delta H was negative. And yeah, enthalpy is not exactly energy, but you understand what I'm saying, right? The change in enthalpy is the heat. So that's why delta H was negative. Consider the equilibrium reaction. Yeah, so it's just an exothermic reaction. Apply the chart. So let's increase in temperature that will just decrease the forward rate. It will just shift backward the equilibrium, right? Yeah. So concentration of N2 and H2 will increase while of NH3 will decrease. NH3 increases now, concentration of H2 decreases now, concentration of NH3 decreases. D is correct. 75D. Question number 76. Which of the following reactions the equilibrium is shifted to the right by increasing the temperature? By increasing the temperature, okay. Okay, so its delta H is negative, exothermic, shifted to the right. So you want an endothermic reaction. Over here too, this thing is exothermic because you have to take energy away from the reactants. B is still exothermic and D is endothermic because delta H is positive. So D will work. Question number 77. Given the reaction, which combination of pressure and temperature gives the highest yield of Z at equilibrium? Pressure and temperature, okay, give the highest yield of Z. So more moles on the left hand side, less moles on, okay, so decreasing pressure will shift to the right. Also it's exothermic, so decrease temperature. So you want the least temperature and the highest pressure. 1000 atmosphere, 1000 atmosphere, right? These two are not good. And 500 degrees Celsius, of course. Wait, you just want the least temperature. So C, 1000 atmosphere and 100 degrees Celsius. Yeah, that should work. So question number 77C. For the manufacture of ammonia by Haber's process, right? Delta H is okay negative. The favorable conditions are right. So more moles to less moles, the same thing as the previous one. Least temperature, delta H is negative, it's exothermic, then that means least temperature and highest pressure. High pressure, and low temperature. So D. 78D. Question number 79. Why are these questions getting easier and easier and easier? The reaction, this thing is enhanced by, come on, seriously. So, yeah, like high pressure, of course. And same thing. All these three questions were the same. So, high pressure, low temperature. Wait, no. Over here it's negative 69 Kelvin. So that means it's actually it's endothermic. That means high temperature and high pressure. Right. So question number 79A. Right. Question number 80. At certain temperature, the degree of dissociation of PCl5 is alpha, starting with 1 mole of PCl5, the total number of moles present at equilibrium. Degree of dissociation of PCl5 is alpha, right? Right, so it's going to be 1 minus alpha. What about, why should we, oh wait, the total number of moles, not just for PCl5, but for everything. So then there's 1 plus alpha, because 1 minus alpha plus 2 alpha, right? 1 alpha for PCl3 and 1 for Cl2. So it's B, 80B. Question number 81. Okay, question number 81. Why is this happening? For the reaction, the equilibrium constant Kp changes with pressure, no, C is incorrect. Catalyst, no. Temperature, yes. So 81D. Question number 82. Consider the reaction something in the closed container at equilibrium at fixed temperature. The effect of adding more PCl5 on the equilibrium concentration of Cl2. Fixed temperature, that's even nice. Closed container, very nice. Well, it's the same question as what we had before, I think, right? We had same kind of question before as well, right? So adding more PCl5, equilibrium concentration of Cl2 will just increase. So B. For the chemical reaction, the amount of X3Y at equilibrium is affected by, yeah, it's affected by the pressure, it's affected by temperature. Yeah, just that. Not catalyst. No, because at equilibrium. So, A. Question number 84. What? These are not even like proper questions. These are just like, these are too easy. How am I supposed to, like, okay, whatever. Question number 84. Consider the following equilibrium in a closed container, something. Okay, at a fixed temperature, the volume of reaction is half. For this change, which of the following statements hold true regarding the equilibrium constant Kp and the degree of dissociation alpha? So, yeah, like this thing is half, right? Your volume is halved. That just means your pressure is increased by 2, right? So at that instant when it is compressed, your pressure will be increased by 2. And increasing pressure, it's just gonna shift backwards. So N2O4, that increases. And Kp and alpha, no, Kp doesn't change, alpha does change. Right, so D. Of course, question number 84D. Question number 85. In the reaction, something equilibrium is established, the pressure of P is doubled to re-establish the equilibrium. The factor by which D is changed is, equilibrium is established, okay. The pressure of P is doubled. So just of B, only for B it's doubled to re-establish the equilibrium. The factor by which D changes is factor by which D changes. What? That doesn't make sense. Like, So you already had some moles and then you added, like, you have even more moles over there, and yeah, something like that, I think. Hmm. Reestablish the equilibrium. Uh, Something's weird about this, like you don't know what the actual equilibrium was. Why is this? Okay, the factor by which t changes. So what assumptions should we be making over here? So first of all, equilibrium is established, fine, and then the pressure of P is doubled. So just for P, and that means you basically are adding more moles over here, hopefully. Yeah, and to reestablish the equilibrium. Re to reestablish, it didn't even change. Like, oh wait, I think it's saying that first equilibrium is established, then D changed by some factor automatically, magic, and then you change the pressure to re-establish the equilibrium, something like that. Because only then can you actually solve it. Because otherwise, we don't know what the initial concentrations are, and it becomes unsolvable, right? You don't know what the equilibrium constant is. You know nothing about it. Yeah. So the pressure of D is doubled. That means D must be increased by square root 2, so that the equilibrium constant, the Kp thing, is still the same. So 85C. Question number 86. The total pressure at equilibrium for the dissociation is 2 atmosphere. If 1 mole of helium is now introduced into the same vessel containing the reaction mixture, the equilibrium constant. Wait, so what we're saying is that it's still in the same vessel. So the volume is still the same. The moles of PCl5, PCl3, Cl2, they are also the same. Their partial pressures are the same. It won't change. Why should it change? Same vessel, right? Yeah, so it remains unchanged. Yeah. If this was in a piston, it was at constant pressure, then it would change, because then helium would take up some pressure, and the remaining pressure would be produced by the other gases combined, and that would mean that the actual pressure on this system, and by system I just mean PCl5, PCl3, and Cl2 atoms, so molecules combined, the pressure on that system actually decreases, and then it would shift to the right. Yeah. So okay, cool. This equilibrium shifts forward if a catalyst is used. No. Low pressure is used. No. If low pressure is used, it will shift backwards because this has more moles. Adsorbent is used to remove SO3 as soon as it's formed. Yes, that's very correct. Small amounts of reactants are used. No, no. Okay, so B, 87B. In the reaction, the equilibrium will shift in the forward direction if so X kilojoule. I think X is positive over here. In that case, it's an exothermic reaction. Then you should decrease temperature. Okay, and what about pressure? Well, it's unaffected because same moles on both sides. So C. Though it's ambiguous, you should say that X is positive. Calcium carbonate dissociates in the following manner. Okay. The pressure of the carbon dioxide. So delta H is given. Oh, okay. So you just apply Le Charges principle. Again and again and again. The same thing. Okay. Calcium carbonate dissociates in the following manner. So it's like it's from solid to solid plus something, some gas. Delta H is positive. Oh, so it needs heat, of course. Uh, Yeah, so it will increase if temperature is increased, the pressure of the carbon dioxide, yes. So it increases if the temperature is raised, yes. Adding catalyst, no. Decrease if temperature is raised, no. Increases if an inert gas is pumped, keeping the temperature constant. What? What? Hey, so it's pumped. That probably means in a vessel, and that means like its moles shouldn't change. So no, D is incorrect. So yeah, like B. No, B is not right. A, right? Increases if temperature is raised. So 89A. In this process, the forward reaction is affected by change in pressure, no. Volume, no. Catalyst, no. Temperature, yes. The equilibrium constant Kv for the reaction is related to the degree of dissociation of A and total pressure Ts. So A gives 2B, huh? Right, so total pressure. Yeah, this is the kind of question where you need to use mole fraction. So let's just do this thing. A and B. Initially, say you had n naught moles of A and you had 0 moles of B. Then after that, you will just have n naught into 1 minus alpha and n naught alpha moles of B. So what's the mole fraction of A at this point? It's just 1 minus alpha upon 1 plus alpha. And that means that, come on. Okay, that means the pressure of A, that's 1 minus alpha upon 1 plus alpha times P, where P is the total pressure. So this is the partial pressure of A. You don't believe me? Seriously? So just use PV equal to nRT. So like the total moles and total times RT is pressure times volume. So it's like this will be the total pressure. And N of A times RT, that is partial pressure of A times P. And then divide these two equations. And then you will believe me. I know you believe me, but like proof, everything needs to be proved after all. So yeah, that's cool. And for B as well, you can have the mole fraction, which is alpha upon 1 plus alpha. Wait, it's not supposed to be, oh yeah, it's supposed to be 2n alpha. That would make sense. If this was just 1 alpha, then this would be 1 and not 1 plus alpha. So now it's 2 alpha upon 1 plus alpha. Cool. And times P, of course, that's the pressure. Right. And you want the equilibrium constant Kp in terms of alpha. So Kp is concentration of P or pressure of P squared. It's 24 alpha squared upon 1 plus alpha squared and P squared upon, and then this guy just without square. There we go. So it's like 4 alpha squared upon, so 1 plus alpha, 1 minus alpha, that's just 1 minus alpha squared, that times P. There we go. Yeah, 4 alpha squared upon 1 minus alpha squared times, not P squared, times P, which is option A. Question number 92. 2 moles each of SO3, CO, SO2 something is taken in vessel if Kc for this reaction is 1 by 9 then. Oh, so 2 moles, huh? Fine. So Kc for this reaction is 1 by 9. Total number of moles at equilibrium are less than 8. Fine. So what's this? SO2, CO, SO. I think this is supposed to be SO3 because yeah, this just got oxidized. This should have been reduced. So SO3, and this is SO2 and CO2. So 2, 2, 2, 2, and then when you change this, like when the reaction happens, well, first of all, as you can see, our equilibrium constant, sorry, our reaction quotient, that is 1, right? And the equilibrium constant is 1 upon 9. That means it's gonna go backward. Plus x, this is plus x, this is minus x, right? And in fact, no, you know what, just use degree of dissociation and stuff. So it's not dissociation but degree of reaction, maybe, if you will. So it's like 1 plus alpha, this is 2 into 1 plus alpha, this thing is 2 into 1 minus alpha, this thing is, yeah, And then the reaction quotient for this thing, that will be 1 minus alpha squared upon 1 plus alpha squared, and that thing is Kc, which is 1 upon 9. Or you could have used 2 minus x as well. It's not a big deal actually. Just thought that might simplify it, but actually doesn't. So yeah, it's like 2 minus x upon 2 plus x is 1 upon 3. Just guess something. X equal to 1. Well, yeah, that works. So x equal to 1, and that means 2 plus x will be 3, 2 minus x will be 1. And this is just 3, 3, 1, 1. Wait a second. Okay, so where was I? Right, so what you want? Total number of moles at equilibrium are less than 8. Total number of moles is 8, exactly. So NSO3 plus NCO2. NSO3 plus NCO2. That is 4. Yes, that's correct. So B is correct. NSO2 upon NCO. That's 1/3. That's less than 2. Yes, it is. So yeah, both B and C. D is the correct option. There we go. Question number 93. 10 mole of hydrogen and 3 mole of nitrogen are sealed in 4-liter vessel. The vessel is heated at constant temperature. At equilibrium, the pressure has fallen to 2/3 of its original value. Okay, H2 and N2. 10 moles of this guy. 3 moles of nitrogen. Take sealed in a 4-liter vessel. Oh, so like the concentration, that will be this thing. The vessel is heated at constant temperature. At equilibrium, the pressure has fallen to 2/3 of its original value. So pressure has fallen to 2/3. That just means the moles have become 2/3 of what they were. Right. So initially they were 10 plus 3, which is 13. Wait, what? But then this is not. So 2/3 of 13. That's weird. Yeah, that is weird. Just fallen to 2/3 of the original value. The numerical value of Kc for N2 plus H2. So it's 2/3 of what it originally was, and that's like 13 times 2/3. That's 26 upon 3. That's how many moles there are. Okay. Say if x is the extent of the reaction, this is like minus x, this is minus 3x, and NH3, that will be like 2x over there, so 2x upon 4, and that means this added up, that's the total number of moles now, right? 26 upon 3, that thing is just the total number of moles after this conversion. That is 13 minus 2x. Oh, this is very weird. That's what it is. So yeah, 2x is just 13 minus 2/3 of 13. Yeah, it's just 13 upon 3. So x is 13 upon 6. So now you know what this thing is. It's like 13 upon 3. That is the moles of NH3. But what do they want? What do they want? Numerical value of Kc for this thing. Okay. So that will be 2x upon 4 squared, and just calculate what this thing is. So 13 upon 16, just put that in there. And that will be 2 times 13 upon 6 times 4. This is going to be bad. So it's 13 upon 3. And that's like 13 upon 12 over there. And then 3 minus 13 upon 6. That's 18 minus 3 is 5. So 5 upon 6. 5 upon 24. Yeah, like that's how it should be. Yes, that's how it should be. Okay, 10 minus 130. Okay, but that's negative. Doesn't make sense. Oh yeah, this is negative. Oh. No, wait, no, it's correct. It's 3 times that, not 10 times. What was I even doing? So this should be 10 minus 13 upon 2, I think, and that's 20 minus 3 is like 7. 7 upon 2. 7 upon 2 upon 4. That's 7 upon 8, and that's what H2 is now. 7 upon 8. So now you got the concentration. We can just find what Kc is from this. So Kc will be, so this is like NH3. This thing squared, right? 13 upon 12 squared upon this thing just 1, and this guy is 7 upon 8 cubed. What question was this? Question number 93. Right, Kc for this thing. So it's this, and yeah, it's definitely none of these. So it's not 1 by 2. This is not 1. It is none of these. So 93D. Okay, question number 94. 94. Consider the reaction in a closed container at equilibrium. What would be the effect of addition of CaCO3 on the equilibrium concentration of CO2? So yeah, no effect. I mean, its activity is constant. It remains unaffected. 94D. Unless of course you already exhausted all the CO3. In which case, yes, it would create more CO2 till of course exhaustion, or till it reaches the equilibrium pressure. So yeah, it either increases or it remains unaffected. And I think 94th it should be B. Question number 95. On decomposition of NH4HS, the following equilibrium is established. Okay, so it's solid that goes to gas and gas. If the total pressure is P atmosphere, then the equilibrium constant Kp is equal to, so the, look at that, it's just equal number of moles, and that means P upon 2 atmosphere, that's the partial pressures of NH3 and H2S. So Kp is just P squared upon 4. Yeah, it was that easy. So 95C. Cool. If pressure is increased on the equilibrium, ice gives water. Okay, which one of the following occurs? Oh, more of ice melts. There is no change in amount of ice and water. More of the ice is formed. Some water gets vaporized. So how does pressure change ice water equilibrium? I mean, like if it was water and vapor equilibrium, that would make sense. Yeah, but ice water equilibrium, I think like water would become ice, because no, how, why would that be? Oh no, this is getting into some thermodynamics territory. More of the ice melts. There is no change in the amount of ice and water. Think, so your delta H minus d delta S, that's what gives free energy. It still remains the same, right? Does change in pressure change your delta H value? I don't think it does. Yeah, I don't think it. And like there is that BDP thing in delta G, sorry, in DG, but seriously, delta H is much more important than those little things. So I think there is no change. I'm going to go with C, but I'm very unsure of this, because this is more about thermodynamics and less about equilibrium. Actually, it is about equilibrium, but it's getting into the thermodynamic territory, and I will have to do some calculations to actually understand what's going on. Okay, the vessel containing the following equilibrium is compressed. This will result in, oh, it's compressed, then that's like its pressure is increased, you could say that. So it just goes back. Increase in the concentration of, wait, if it is compressed, then its concentrations already got increased by twice. Yeah. What, increase in the formation of NO2? No increase in the concentration of NO2 or N2O4. No, that's just wrong. Change in the equilibrium constant. That's wrong. Increase in the formation of NO2. Uh, no, no, B is not correct. It like you could think it's going back, not front. And even if NO2 did change its concentration, its moles are the same, right? And then it would go back. So it's actually decreasing. Increase in the concentration of N2O4, yes, that's for sure. In both ways. Question number 98. In each of the following reaction, pressure has no effect on the equilibrium. So A, no. C, yes. B, no. D, no. So 98, C. Question 99. An exothermic reaction which proceeds with decrease in volume will give maximum yield at. Exothermic reaction proceeds with decrease in volume. Oh, so like it's moles basically those decrease. And I think it's at constant pressure. Wait a second. It has decrease in volume over there. So it once again goes to the thermodynamics territory once again. Oh. So yeah, like you could think of it as being gases and stuff, but then in the end you just have to know about like that thermodynamics. So let's actually do it, right? So you know that delta G is given by this thing RT natural log of Q upon K, right? But delta G at the same time is also delta H minus T delta S. Actually, no, instead of doing this, just go for delta G directly. So this is a delta G of a reaction, right? So this is the delta G of going from the reactants to the products. And for a phase change, there's only one reactant, one product. So for example, if it's ice and it's going to water, then the delta G for this thing is the Gibbs free energy of water minus Gibbs free energy of ice, and this is like per mole the Gibbs free energy, right? And that's what this thing is. Now if you change this, so and notice this is like there is no such thing as a reaction quotient for this, or like equilibrium constant or whatever. So there's only one criteria, that it is either completely like reversible or it's spontaneous in either of the directions, right? So it's like either the ice will completely melt away, or it will freeze like all of the water. So there is no this term for phase changes like these, right? So because Q and K, those don't matter, they are all constants. So this is the Gibbs free energy for this reaction, and we know for reversible reactions that is at equilibrium, you should have this Gibbs free energy being equal to 0. All right, so now there's like some initial conditions, so we'll denote that by naught. So this has G ice naught and G water naught, and you change this, so this is at pressure P naught, and now at some pressure P, you also have some temperature T naught, and this is at temperature T. So this changed, its Gibbs free energy is now GW and GI. So what was this change actually? So for this thing, you could maybe form a reversible reaction from this state, sorry, reversible process from this state to that state, right? Such that you are changing your pressure and temperature, right? There could be a reversible process like this. So for that, you just have dg equal to, well, it's like dh minus dds, and dh is just dq minus dds. Or in fact, no, like it's not at constant pressure temperature anymore, so it's not that. So dh is just d of u plus pv, right? And yeah, like u plus pv is like du, and for pv like dpv, that will be PdV plus VdP, and then minus TdS. Actually, no, I should say dTs. So then this will be minus TdS minus SDT. And you can write du as dq minus dq minus pdv, right? So minus pdv is just the work, the infinitesimal work, and this thing, and yeah, so this cancels with that. dq cancels with it cancels with tds because it's a reversible process from here to here, only from here to here. All right, not this is not necessarily reversible, but we designed this process to be reversible, and that means we can write this thing as vdp, right? Yeah, this thing remains. This is not gone, like it's gone. We wrote it like this, right? Minus sdt. Okay, so now we know what dg is. Now the cool thing about liquids and solids is that their volume stays constant and their entropy also kind of stays constant, right? And in fact, in this case, we are not even talking about temperature really. So we could like just say this is the same thing, and then SDT, like T would just be 0. So hey, look at that. This term is just gone. So for constant temperature, what you have is that if you're going from this pressure to this pressure, you just have delta G. So I should say like GW minus GW naught. That will be the molar volume of the liquid, in this case water, times the change in pressure. So it's like P minus P naught. And similarly for ice, it will be G ice. It should be G ice minus G ice standard, whatever that standard condition was, is the molar volume of ice times P minus P naught. And that means when you subtract these two equations, so you have GW minus GI, that thing is just delta G and minus delta G standard. That thing is P minus P naught times VW minus V ice. And yeah, now I can explain things more clearly. So if your change in volume is positive, then changing pressures, like increasing pressure, that will make this thing positive, and that means your delta G will become more positive. And that's not what we want. So if your change in volume going from say ice to water, that thing is positive, then you should try to decrease pressure. So when you decrease pressure, your reaction will go forward, right? So delta G will become more negative. So now we can go back to that question, right? So it was question number 96. If pressure is increased on the equilibrium ice to water, then which of the following occurs? So for ice to water, you know that ice has, like water has this anomalous property that the molar volume of ice is more than the molar volume of water, which is, yeah, like it's very weird, but that's how it is. So what that means is that this thing actually is negative. Yeah, this thing is negative. And like wait, at what temperature, because it changes, right? Well, yeah, it changes, but in the end it's just that. So this thing is negative. So if we want our delta G to become more negative, we should want this to be positive. So you want to increase pressure. So if pressure is increased, more ice will melt to water. And this is actually contradictory to what we thought before. What we thought was that water would freeze to ice, like water vapor comes down to water. The same thing should happen to water. But then it's like this is just inversed because of the anomalous properties of water. So yeah. So more of the ice melts. And hey, this is actually like there's a very famous experiment or whatever that thing, like it's a practical, where you have this block of ice and you just put a very heavy block with a string on this block of ice, like maybe like this. You got two blocks, these are very heavy, and you have this block of ice on maybe a table, for example, and then this string cuts through the ice completely. So at first it holds, but then it melts actually, and then this starts seeping inside and it goes all the way to the bottom. So that represents this calculation that yes, changing the pressure, increasing the pressure in this case, that will favor the forward reaction now. So there we go. Question number what? Question number 96. That should have a. So yeah, if there wasn't more questions on this thing, I would have done this later, but there were more questions. So it's not C, it's A. Okay, question number 99. Exothermic reaction which proceeds with decrease in volume. So your delta V is negative and it's exothermic. Well, that's related to temperature. We won't be dealing with temperature for now. So decrease in volume, like melting of ice, for example. So it will give maximum yield at high pressures, of course. So you want high pressure, and of course it's exothermic, so you want low temperature. So for ice, you want high temperature, but for this guy, you want low temperature. So 99C. And finally, question number 100. For which one of the following reactions is a combination of high pressure and high temperature helpful in obtaining a high equilibrium yield? So high temperature, that means endothermic, and high pressure, right? High pressure, that means your, okay, cool. So I got it. So yeah, this has high pressure over there. And is this endothermic? It is, in fact, because it's like negative some energy. So this works. So these are not delta H values. These are just like this gives off that much of energy, something like that. So it's negative delta H if you want, I think. Okay, so first of all, you want high pressure to give high yield, and that means this works. A works, okay. C also works. B works, yes, and D doesn't work. So between A, B, and C, and you want high temperature, that has to be endothermic, right? Oh no, wait, A doesn't work. I didn't see that 3F2 first. So it's only between B and C then. And that means C is the winner because this has positive heat involved, so it's exothermic, not good. C is the one. Okay, so that's it. Now we'll just check the answers. Okay, keep on going. Foundation builder. All right. So 100. Let's see. And like for 100 questions, do I really want to check answers? I don't know. Just take a snapshot of it and you check answers yourself. If there's something wrong, tell me in the comments. Yeah, whatever. So I'll see you guys in the next video.